Alright, today we are working on Newton's second law of motion, the lab, and I have set up the majority of what is going on for this particular lab. We've leveled the tracks, we've placed our motion detector to place so that it is parallel to the track. We've attached our pulley and made sure that it is beyond the edge of the table so that our hanging mass is able to fall to the ground. We've already got our computer set up and all of the other fun stuff. The next thing we need is to find the mass of the cart and the hanger. So we've got our scale here. There's our cart. And our mass on there is exactly 550 grams. When we convert that to kilograms, it gives us 0.550 kilograms. When we look, that's the combination of both. If we look at just the cart, it was 500 grams exactly, so that was 0.500 kilograms, and my mass hanger is 51 grams. So 0.051 kilograms. All right. So now we are able to move on through our process. All right. So we got our cart on the track near the motion detector. Our string is going to go over the pulley, and our mass hanger is going to be suspended from the string, like in the picture. Then we're going to have 5 10 kilogram slotted masses. So I have my 5 10 kilogram slotted masses. Oops. Mass hanger over the pulley, and I am ready to start collecting data. Unfortunately, I collected a little prematurely. Alright, so when I hit collect, the motion detector is going to make a sound. I'm going to let go. My cart will accelerate and hit the end of the track. So we have some data on our screen. That is the data that we recorded. So this portion is where, before I let the cart go, we have it smoothly accelerating, and then this is where it hits the end of the track. So during the acceleration point, which is where we see our change of velocity here, we are going to highlight that data. And we are going to click on the linear fit button. When that happens, our data comes up with this, and we are given a slope, and that is our acceleration. We are going to continue the same process we just did, except for the fact that each time that we run the trial, we're going to take one of our 10 gram masses and place it on the mass hanger. I've gone ahead and already moved one of mine. I can hang it. I've completed all of my trials at this point. Notice I went ahead and updated my suspended mass. Each time I moved a slotted mass from the cart to the hanger, I went ahead and updated that. my total mass of my cart and suspended mass does remain the same the whole time. This comes from the 500 kilograms of the cart, the 5.5 kilograms of the cart, the 0.051 kilograms of the empty mass hanger, and then the additional 50 kilograms from the 10 gram discs. The acceleration I did get from the slope of the velocity versus time graph off of the computer. The applied force column is currently blank. The applied force is coming from the suspended mass because the suspended mass is pulling the cart across the track. So in order to get the applied force, we're going to take this mass in kilograms and multiply it by 9.8, since it does have, it's the weight of the mass that's actually causing that. Next, we're going to move on to data table 2. For data table 1, when we were doing our collection, we kept the total mass of our cart and suspended mass the same. For data table 2, what's going to end up happening is our suspended mass is going to remain constant, but our total mass is going to change. We're going to see what happens to our acceleration as a result. So now I have my full column of my suspended mass, which remained constant the entire time. My total mass of the cart and of suspended mass, which increased by 100 each time I ran a trial. And then the accelerations that I collected from the slope of the velocity versus time graph. Now that you have the chart, you can find the applied force by multiplying your suspended mass column by 9.8. That's going to give you everything here. And then you are able to perform the rest of the tasks here on your own. Happy labbing!